on the integral test. So this is going to be another test for trying to decide whether a series converges or diverges. And the strategy is going to be that we start with a series, we represent the sum or interpret the sum as a sum of areas of rectangles. And then we consider that those rectangles either below a curve or above a curve. So the areas of the rectangles are going to be either bigger than or less than the area under the curve. And the area under the curve is an integral. So we can relate sums and integrals, at least come up with an inequality, even if they are not the same. So let's see some examples how it works, and then we'll see what the theorem is supposed to be. So our first example is, does the sum of 1 over n squared converge or diverge? So 1 over 1 squared, 1 over 2 squared, and so on. And we compare it with the underlying function, which is 1 over x squared. So let's see them on a graph. So here is y equals 1 over x squared. And now we're drawing right rectangles in this case. So the width of the rectangles is along integer points. So we have a rectangle from 0 to 1, 1 to 2, 2 to 3, and so on. And by a right rectangle, I mean that the height of the rectangle is the value of the function of the right endpoint. So here, for instance, this first rectangle, the height is the value of the function at 1, which is 1 over 1 squared. And the width of the rectangle is 1. So this is area 1 over 1 squared. From 1 to 2, the height of the rectangle is the value of the function at 2. So that's 1 over 2 squared. The width is 1. So we get an area of 1 over 2 squared. And so on and so on. So we have areas of rectangles which are 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, and so on. And so the sum of the areas of these rectangles is exactly the sum that we're interested in. So that's what we're trying to understand. And clearly they lie underneath the curve. So the areas of the rectangles are going to be less than the area under the curve. So the sum is going to be less than the integral. That's the idea. Okay, so let's formalize that. So how do we do that exactly? So let Sn be the nth partial sum. So remember we said a series converges if and only if the partial sums converge. And let's try to estimate Sn. So Sn is the sum of the first n rectangles in the picture. And we can estimate that using the area under the curve. So we could just say, Sn, it's the sum of the first n areas of the first n rectangles. We could just say the rectangles lie below the curve. So the areas of the area of the rectangles is less than the integral. But if we just estimate by the integral directly, then we're going to come up against a problem, which is that here on the left from 0 to 1, 1 over x squared has an infinite asymptote. So that would not be something good to compare it to, because from 0 to 1, the function 1 over x squared is going to blow up. We're going to get something that's infinity for the area under the curve over here. So that would be a bad idea, but the area of the rectangle from 0 to 1 is just a finite piece. So let's just keep that finite piece and then estimate the rest by the area under the curve. So that's the idea. Okay, so Sn, we keep the first rectangle, and then we estimate all the other rectangles by the area underneath the curve. And the advantage of doing this is that we get something that's way easier to compute. Right here is x to the minus 2. The antiderivative is minus x to the minus 1. We plug in n, we plug in 1, we subtract, we get 1 minus 1 over n. And then we add the 1 from before, we get 2 minus 1 over n. So here we have an estimate for the sum of the areas of the first n rectangles. We can say that at least it's less than 2 minus 1 over n. So in particular, it's always less than 2. So now if we think what happens to the limit of Sn, remember the sum of a series is the limit of Sn. Sn is bounded above by 2, and it's increasing because we're adding on more and more terms as n gets larger. So Sn is an increasing sequence that's bounded above by 2, hence it's going to converge to a number that's less than 2. Okay, but talking about the convergence of Sn and converging about the series and talking about convergence of the series are the same thing. So the series is going to converge to something that's less than 2. Okay, so here was the idea, very clear hopefully in the picture, right? The sum we're interested in was the sum of areas of these rectangles. The rectangles lie below the curve. We can estimate the area under the curve as an integral. And that integral is finite, so we can say that the sum of areas of the rectangle is finite. And there was only one piece that we had to worry about from 0 to 1. We split that off and dealt with that separately because we didn't want to include this infinite asymptote of the curve. Okay, going the other way, what about, say, the sum of 1 over square root n? 1 over square root 1, 1 over square root 2, and so on. Let's compare it with the integral of 1 over square root x. But now this integral diverges. So we might hope to show that our sum diverges. And if we want any chance of showing that something diverges or that our sum sums to infinity, we want to have the rectangles lying above the curve. It's no use to have them below something which is going to infinity. We have to have them above something going to infinity in order to say anything. So in this case, we're drawing left rectangles. So meaning that, say, from 1 to 2, the height of the rectangle is the value of the function at the left endpoint, so that's 1 over square root of 1. It's 1 by 1 over square root of 1, so we get area 1 over square root of 1. The same thing from 2 to 3, 3 to 4, and so on. So here again, we have rectangles, whose areas are the terms in our sum. So we're interested in finding the sum of areas of these rectangles. And now because we've drawn left rectangles, these rectangles lie above the curve. So we're going to have an estimate going the other way. So let's do that. So Sn is the sum of the first n rectangles, it's the partial sum. Okay, the rectangles lie above the curve. So the area of the rectangles is going to be larger than the area underneath the curve, which is the integral from 1 to n of 1 over square root x. This we can calculate exactly, finding the antiderivative, plugging in n, plugging in 1 and subtracting them. We get 2 square root of n minus 2. That goes to infinity as n goes to infinity. So Sn is larger than something that goes to infinity. Sn is also going to go to infinity. Okay, so that says that the sum of 1 over square root n diverges. Remember, saying something about a sum or an infinite series is exactly the same as talking about the limit of the partial sums. So just going back to the picture, why did I switch from left endpoints to right endpoints? So here we have left endpoints because we are trying to show it's larger than something that diverges. If we had chosen right endpoints, then the rectangles would have been below the curve, but the area underneath the curve would have been infinite. So we would have had a sum which is less than something that's going to infinity. Okay, that wouldn't tell us anything. So we want to do it the other way around so we can at least say it's larger than something going to infinity. So that was why we switched from left to right, or vice versa. Okay, so what's the underlying result here? It's called the integral test. So suppose we have a function which is continuous and positive and decreasing. So like 1 over x to the p that we saw in the previous examples. And we have a and is f of n. So the terms in our sequence in our series come from such a function. Then the sum will converge if and only if the integral of the function converges. So rather than calculating or trying to figure out whether the sum converges, we can just check these conditions and then look at the integral instead. And this is good because we saw lots of tools, right, for finding improper integrals, whether they converge or diverge. For instance, we replace infinity by t, work out the answer in terms of t using antiderivatives, and then take the limit. So this is on the right is something we can do. Okay, and this does go both ways. So if the integral converges, then the sum converges. If the integral diverges, then the sum diverges. So this is very satisfactory. Keep in mind, we can swap the n's to different numbers. So it could start at 2, could start at 3. It doesn't really matter. But it does not say that the sum and integral are equal. So this result is based off comparing the area of the rectangles and the area underneath the curve. And in the simple pictures we draw, right, they are not the same areas, but one area lies beneath the other. So they are not the same, but at least it's telling us that one is finite if and only if the other is finite. But for instance, the sum of 1 over n squared is pi squared over 6. This is not easy to show, but it can be shown. But the integral of 1 from 1 to infinity of 1 over x squared is just 1, and that is something you could show quite easily. So the sum of 1 over n squared and the integral of 1 over x squared are not the same, but one is finite if and only if the other is finite. Okay, and it also works if f is eventually decreasing. It doesn't have to always be decreasing. But most of the examples you see will be. So one application of this is we can finish classifying the p-series. So the p-series sum of 1 over n to the p converges for p strictly bigger than 1 and diverges for p less than or equal to 1. So we saw this with p equals 2, right? We saw a couple of slides ago that 1 over n squared converges. This is p equals 2 bigger than 1. And we saw that the sum of 1 over squared n diverges. That was p equals a half, which is less than or equal to 1. Why is this true? So it's an application of the integral test. Right, if p is strictly bigger than 0, then we can say that 1 over x to the p is continuous positive decreasing. Right, it looks like 1 over x squared, 1 over x cubed, 1 over square root x, any of those functions. It's continuous positive decreasing. So by the integral test, the sum converges if and only if the integral converges. So we can look at the integral instead. And the integral from 1 to infinity, 1 over x to the p, that's just the p-test for improper integrals of type 1. So we said that converges if p is strictly bigger than 1, diverges for p less than or equal to 1. Okay, but here we were assuming that p is bigger than 0 in order to be able to do the integral test. So we finished classifying at least as long as p is strictly bigger than 0. But if p is less than or equal to 0, you can easily check that 1 over n to the p does not go to 0, so it diverges anyway. So that fills in the rest of the cases. Okay, so bottom line, this is just an application of the integral test and the p-test for improper integrals of type 1. Okay, another problem we have is that the integral test tells us whether a sum converges, but it doesn't tell us what it converges to. So how are we supposed to estimate at least what it converges to? And one way is if we have an infinite series that's converging, we're trying to sum up infinitely many terms, all of the terms. How could we get an estimate? Well, the best estimate we could do is to add up 100 terms, or add up 1,000 terms, or add up 10,000 terms, is to add up a lot of the terms. So that means we're finding Sn, the partial sums for large n. That's our best way to estimate. But if we have an estimate, we quite often want to know how good our estimate is. It's going to make a big difference whether our estimate is within 0.01 or whether it's within 10,000. An estimate within 10,000 is not very good. So in order to say whether we have a good estimate or not, we have to be able to study the error or the difference or this thing called the remainder. So this is Rn. It's the difference between the true value of the sum S and the value we get if we add up only n terms together. So S minus Sn. If we think about what we're missing, if we only add up the first n terms, we're missing the n plus first term, the n plus second term, the n plus third term, and so on. So we need a way to understand how large this is. So there is a remainder estimate based on the integral test, based on interpreting these things as sums of areas of rectangles and comparing to areas under the curve. So basically we're saying, suppose we have a sum of AK, which converges, and the reason that it converges pretty much comes from the integral test. So the terms come from a function which is continuous, positive, and decreasing, at least for x bigger than or equal to n. Then we can have this estimate for the remainder. We can say the remainder Rn is less than the integral from n to infinity of f of x dx. There is also an estimate from below. It's bigger than the integral from n plus 1 to infinity of f of x. But quite often we're interested in showing the remainder is small. So if we want to have the error or the remainder small, then it's going to be useful to check that this integral on the right is small. Because if this integral on the right is, say, less than 0.1, then the error is even less. So the error is going to be less than 0.1. Okay, so let's see an example where we do that. So we're going to approximate the sum of 1 over n cubed using the sum of the first 10 terms, and then estimate the error involved. And then we want to study how many times we need to estimate the sum to within 0.0005. Okay, so if we want to estimate the sum using just the sum of the first 10 terms, there's only one thing we can do. We have to add up the sum of the first 10 terms. So 1 over 1 cubed, 1 over 2 cubed, up to 1 over 10 cubed, and so on. If you work these all out, plug them in a calculator, obviously we'll give you something nicer in an exam. You'll get around 1.197532. If we want to estimate the error involved, so here we added 10 terms. The error if we add only 10 terms is exactly R10. It's the remainder if we only use 10 terms. So we have to estimate R10. And we said that Rn is less than the integral from n to infinity of the function. So R10 is going to be less than the integral from 10 to infinity of our function, which is 1 over x cubed. Okay, this we can actually do. We find the antiderivative, plug in t, plug in 10, subtract them, let t go to infinity. We will get in the end 1 over 200, which is 0.005. So if we use 10 terms, we get this estimate, and the error is at most 0.005. That's a pretty good estimate, so we wouldn't be disappointed with that. Okay, going on to B, how to make the sum to within 0.0005, so another decimal place. In other words, we want to know how many terms, we want to know how large n should be in order to make Rn less than or equal to 0.0005. And there is no way to calculate Rn exactly. So the best we can do is to have Rn less than something, which is itself less than 0.0005. So we know that Rn is always less than the integral from n to infinity of 1 over x cubed, and that's 1 over 2n squared, if you follow the steps to calculate the integral. So if Rn is less than 1 over 2n squared, and we want to make Rn less than 0.0005, one way to do it would be to make sure 1 over 2n squared is less than 0.0005. So that's our strategy. We want 1 over 2n squared less than 0.0005, or if we rearrange, we'd see this makes n larger than the square root of 1,000, which is around 31.6. Okay, so if n is supposed to be a whole number and it's supposed to be larger than 31.6, we should take n equals 32. So we need 32 terms. Okay, so here was the idea. In both cases, we're just using the simple fact that Sn should be a good approximation for the full sum if we add enough terms. How many terms? That's the remainder Rn. And we have a way to estimate the Rn from above. So we can either find out how large Rn is, find an upper bound, or if you want to make Rn small, we can make the thing that's larger than Rn, make sure that's small instead. Okay, lastly, how do we find a range for the sum? So, we know that the sum is close to Sn plus or minus something. You can add on to get a range for where the true sum lies. So under the same conditions as before, we can always say that the value of the true sum, so S, the true value of the infinite sum, lies somewhere between Sn and the integrals on the left and right. So somewhere between Sn plus the integral from n plus 1 to infinity and Sn plus the integral from n to infinity. And the advantage of this is that S is pretty much impossible to calculate unless you have some very particular sums like geometric sums. But Sn is always something you can calculate just by brute force, just by adding up a bunch of terms for the first n terms. And the integral from n to infinity is usually something you can calculate using all the tools that we talked about in the improper integrals section. So the left and right we can calculate, that gives us at least an estimate for what is in the middle. For instance, if we apply this to S, which is the sum of 1 over n cubed, with n equals 10, just plugging in everywhere, S is the sum of 1 over n cubed, and plugging in n equals 10. It's going to be between S10 and the integral from 11 to infinity, or S10 and the integral from 10 to infinity. Okay, S10 we already computed, or I already gave a couple of slides ago. These integrals we can compute explicitly. So just evaluating everything on the left and on the right, we get that the sum of 1 over n cubed is between 1.201664 and 1.202532. So that's, even though we haven't computed the sum explicitly or exactly, this is not at all a bad approximation for the sum, right? So it lies somewhere inside this interval where the things on the left aren't on the right, we can calculate. Okay, just to wrap it up, so we talked about the integral test, which says that if we have a series where the terms come from a function which is continuous positive decreasing, then instead of trying to understand whether the sum is convergent or divergent, we can look at the integral because they behave the same. And then we had some estimates for remainders based on that. So if we want to estimate the sum of a series, we can just do Sn for large n. That means we need to estimate the remainder Rn, and we had some ways to do that using integrals as well. Okay, thanks everyone, see you.